Okay, well. As soon as I started recording, this thing zoomed back to where I don't want it to be, so hang on a second. Okay, that's pretty good. At least the camera was in the right position. Okay, so here I've got some dominoes. You know what's going to happen. I'm going to slowly nudge this domino till they all fall. And what I'm really interested in modeling is how fast does the progression proceed? In other words, what's the velocity of a point will keep up with the latest falling domino, okay? So kind of what's the speed of the chain reaction? And how does that speed depend on the spacing of the dominoes and even the thickness of the dominoes? Turns out it's fairly complex. Okay, there it went. How fast was that? How long would it have taken that chain to get to the end of the room? It's hard to tell because that went really pretty fast, probably in less than a tenth of a second. So it's hard to judge. That turns out we can pretty easily measure it. We just make a series of dominoes, a meter, maybe 2 meters long. Measure carefully what the distance is between them. And do one of several things. Of course, we use audacity, but that's cheating. Okay, and we will, but we're going to see what our more sophisticated results are. We'll use a pendulum. Let the pendulum swing, pull it back, release it, let the pendulum start the first domino and count half swings of a pendulum till the last domino falls. Did that. I think there are 3 half swings of a 1 second pendulum around a meter. I didn't actually measure it, so it looks like about a meter. So I'm estimating it's between 40 and 80 centimeters per second, giving myself a lot of leeway. I don't think it changes much with the spacing of the dominoes, but it definitely should change, I think. I haven't done the analysis. Okay, so to start the analysis, we just consider one domino falling into the other. And we assume that the dominoes are infinitely thin and constrained at this point so they don't slide on the surface. And we could use a high friction surface and avoid sliding. Okay. So here's one domino. Here's the next domino. Now, presumably this domino has been hit by something, so it has some initial rotational velocity. Okay. And as I mentioned, everybody, I dialogue with ChatGPT on this, just to see if it had anything to add to what I was thinking. Okay. And it turns out it kind of didn't, but it did. It waved its hands and say, yeah, well, this isn't really, yeah, I prompted it. Is this really an isolated system? Okay, it isn't. Because whatever is constraining this thing, whether it's friction on your surface or some kind of an axle that it rotates about, is exerting an external force on the system, 2 dominoes. And that becomes important and relevant. And one thing I did think of in the process of trying to get ChatGPT, I was using GPT 2.5. I don't want to use GPT 4 because it's too good. GPT 5 makes all kinds of mistakes. Okay. I felt like I was talking to a physics student who had all the formulas but didn't know what to do with them, which is kind of typical. I was that way. Everybody is that way as they're learning. Well, anyhow, so we give these things a length, call the length L, call the spacing A, whatever. Give it an initial velocity. This thing falls and hits this one, which then is given a velocity because of the collision. Hits the next one and so forth. If we can analyze this in terms of the initial angular velocity of this domino and the time it takes to start this domino, okay, which is basically the time it takes to fall from here to here, given the initial angular velocity, then we can model the whole process as a first approximation. Now, there are other things, and with the real dominoes aren't infinitely thin. Okay. So we can just start with this because it gets more complicated if the domino is pivoting on a point on its edge, which is rounded, which makes it even more interesting. Okay, so there's a lot of stuff to do, but just starting with this model, I know the initial angular velocity here and the spacing. Can I find the initial angular velocity this is going to get? Can I find an angular velocity here that'll match the angular velocity that this one gets from it? Okay. Because that's kind of what's going to happen in a long chain. Everything's going to become uniform after a transient phase. Okay, well, that's just kind of a warm-up. That's the model we want to look at. I will comment that as this thing falls, it's got an angular acceleration. You know, the particles up here move a lot faster than the particles here or the particles here. So this thing has a moment of inertia, has an angular acceleration that's given by the torque. The torque let's call this force negative mgj. And let's call this your r vector. So the torque equals r cross negative mgj. Lay a torque into the board, having to accelerate in the counterclockwise direction, which is the negative direction for acceleration. Put this in 3 dimensions. You got I, well, you got, let's say, what do I want? We'll just do I, J, and K out of the board. Okay. So the cross product here is going to be a multiple K. I'm not telling you everything because I just want you to think about the idea. We see that the cross product is going to increase as the angle approaches horizontal, because the cross product has magnitude of R times the magnitude of the force times the sine of this angle. Sine of that angle will be increasing. Or another way to look at it, if you think of the moment arm as being this vector, well, that's just R sine theta, isn't it? Perpendicular to this. The most direct path from the axis of rotation, opponent rotation, to the line of action of the force. All concepts that were amply covered in the chapter on angular momentum and stuff. Okay, make sure you know those things, and try to get some of that, you know, review some of that before lab 2 days hence. Thanks. We want to actually measure this, and then I'm going to ask you to analyze it. Good chance something like this is going to appear in the final too. Okay. Now let's go on to simple harmonic motion. We sketched the whole thing pretty much at the end of class last time. I think I might have left out a negative sign on the force law. And of course, it's obvious that we need it. But let's just start with talking about the condition for simple harmonic motion, which is you have a linear restoring force. Okay, so or from a linear restoring torque. If you suspend one of these beams from a rubber band, wind it up, rubber band will unwind. The more it's wound, the more force you get, the more torque you have. Okay, so the torque will be proportional to how much you wind it. So you can have then a simple harmonic motion. These beams do undergo a simple harmonic motion also spontaneously because they're a little unbalanced. We'll take a look at that. Okay, so you basically have a few examples of simple harmonic motion. Let me just pull out a few examples, which I can do very quickly, I think. Okay, here the system is at equilibrium, and I can't see my screen, so I don't know if I'm holding it up so that you can see what I'm doing. Okay, I think it was. Okay, yeah, I've got to get up a little higher. Okay, so this is it's oscillating a little bit, but it's pretty much it's in vertical equilibrium. So right now, the tension in the rubber band chain is equal and opposite to the force exerted by gravity. If I pull this down, okay, it rises and oscillates. I was actually helping it a little, trying to, stimulate it at its natural frequency. Make sense? That's a simple harmonic motion. And to a fairly good approximation, the force that the rubber band exerts is proportional to how much it's stretched. Right now, the force of the rubber band is equal and opposite to the weight of the hanging mass. So I pull it down here and pull it down that much further. Should be exerting about twice the force there as it was, okay? So exerting a force here, go twice as far as exerting a little more, twice the force, and 3 times the force. And when it does that, it tends to oscillate, and it tends to oscillate with a constant period. Okay, the period doesn't change much. Now, if I just let it damp out, let the oscillation damp out, period will change a little bit because the rubber band does not exert an exactly linear restoring force. We're going to measure that. We'll measure that in Lab Friday too. Okay, so that's one example of simple harmonic motion. Another example, that's not going to work all that great. Okay, let's see, we've got. Okay. Oh, all right. This magnets are downright stalling. Okay. Too much stuff here. Okay. I think I've got it all 3. All right. Now we're familiar with the rotation of this beam. But what happens when it comes to rest? It tends to go back where it was. Actually, I'm not holding it still. So, oh, wait a minute. I got the stupid weight on here. Hang on. It's not stupid weight. Okay, there we go. Now, it goes out here, comes back, goes back. Well, that's a simple harmonic angular motion. If we set this on a tabletop and measure the period of that motion, it's going to tend to be reasonably constant. Okay. Another example, and what did I do with my rubber band chain? Everyone else had a rubber band chain. And I got too much stuff laying around here. Oh, there it is. Okay. Set it down carelessly. Okay. Another example of simple harmonic motion, or nearly simple harmonic motion, is a pendulum oscillating back and forth. Now, this thing hanging from a rubber band is not a very good example of a simple pendulum, because due to the fact that this thing's moving fastest here, it requires the greatest centripetal force to hold it in what would be a circular arc. If this string or this rubber band wasn't stretching, you can see if I release it, that the centripetal force results in a vertical oscillation as well as a horizontal one. But if I do just a very small oscillation, this thing is going to oscillate at a very nearly constant period. So what's going on in all of these cases? Well, in all of these cases, the net force is a constant, negative constant multiple of x, x being position with respect to equilibrium. What's equilibrium? Well, if you remember from previous chapters and previous analysis, equilibrium is a point where you have zero net force. Okay, well, if x is measured with respect to the equilibrium point, then x is equal to zero at equilibrium, and that's when you have zero force. So x equals zero has to be the equilibrium position if this law holds. Okay, if this law holds, or if tau net equals negative k times theta, which theta is your, theta being your angular position measured with respect to equilibrium. We're going to get simple harmonic motion out of this. Now, you know the energy considerations. You've been through that. You've done springs and I think even pendulums. So you've seen all the energy relationships for this kind of a force. We'll derive it anyway. But that much you should be able to build on. So we can do this whole simple harmonic motion thing, which is one assignment. Okay. If, and I did this last time, I'm not using the vector form here. You get this differential equation. You know, net force is mass times acceleration. Acceleration is the second derivative of your position, and so forth. And that's a simple linear second order differential equation. Okay. And your solution is both of these forms are useful in one form or another is probably the more useful in a given situation. And the assignment, my lab assignment, whatever you call these things, does a nice job of showing you situations where this is better situations where this is done. I'm just going to indicate that this and this are arbitrary constants. You have a second order equation, you get two arbitrary constants. It's obvious that B and C would be arbitrary constants. It's obvious if you plug in cosine of omega t for x, second derivative is negative omega squared cosine omega t. And I didn't say omega as I did last time. Omega is the square root of k over n. So it's very easy to verify this or this as a solution to the equation. And of course, you know differential equations well enough to know that you trial solution a e to the I omega. IRT, I think, is the variable that's usually used. You do a trial solution and you come up with this very quickly. Okay, I think maybe when I wrote this down the other day, I didn't put the negative in front of the kx when I wrote this law. But there it is. Okay, so right there, that's your equation of motion, either this or this. So now I'm going to make this into a vector again, and I'm kind of waving my hands about that. The details. You can get your velocity and acceleration function just by taking derivatives of this or this, or both. Okay. So all that comes out very, very simply from this premise. This is where we start. This implies this by these simple steps. There we have it. So practically, what can we do? Well, we'll do it in lab. We can measure the length of a spring. Now, I'm not going to use a spring because rubber bands are just so handy. Okay, and they're cheap. Okay, so, and they're more interesting because they clearly do have some variation from linearity. Force is not exactly a linear function of length, but yeah, I've got a length here, okay? I add a mass, a known mass, I think that's 20 grams. And this thing gets a little bit longer. And I add 20 more grams. And it gets a little longer than that. But come on, this is way easier threading a needle. Okay. So I can just measure the length. From those two measurements, if the rubber band is linear, I can easily determine K because I have two values for X. Okay. And I have two values for the force. It's a linear relationship. That's all I need. Now for the rubber band, we're going to do more than that because it's not completely linear. And we're going to see that even though it deviates significantly from linear, This model still works pretty well. Problems you'll see basically tell you, okay, this spring has this length when it holds this much weight, and this length when it holds this much weight. Now we're going to put this weight on it. How's it going to oscillate? What's its position function? What's its velocity function? What's its acceleration function? When is it at this given position? We just set the position function equal to that given position and solve it. Simple equation. You know the trig. So it's going to be very easy to solve those equations. Conceptualizing and so forth can be a little more challenging. Okay. In class last time, we have a picture that models this entire phenomenon. Okay, there's a reference circle. Better than my usual circle. Perfect. Okay, and there's kind of where I think the center is. You know, this is a reference circle. Then we'll do this for x equals a cosine of omega t plus 5. This is the form that relates to the reference circle. Now, it should be obvious that using trigonometric identities and so forth, it's easy to go from this form to this one, okay? Or vice versa. Sum of two angles formula for the cosine gets from here to here. And also gets you from there to there, usually in the opposite direction. Okay, the reference circle has radius A. Put two arrows on this thing to indicate that it's not a vector. Okay, and I'll agree to draw my vectors all in color. Okay, this, if you wish, is your x-axis. And of course, you've also got a y-axis. But the angles are all measured with respect to the x-axis. Phi could be any angle. Let's just say that this angle is phi, and omega t is this angle. Then x equals a cosine of omega t plus phi. Well, this angle from here to here is omega t plus phi, right? So this whole angle is omega t plus phi. So what is x? Well, by the unit circle definition, this is x. Now, x is a vector. I'm going to treat it as a vector. And as t increases, omega t, assuming omega is positive, you continue to move around the circle. And what's going to happen to the position x? Well, if we start here, by the time we get down here, x goes all the way from the center to the circle, right? So x is going to get bigger. Then as we go down to here, well, X is just a projection of this point. That point is going to give you X equals 0, isn't it? Then as we move from here to here, X will increase. As we move from here to here, X will decrease again. As we move from here to here, X will again increase, but in the negative direction. Okay? Make sense? So that as we go around this circle, I think I'm coordinated enough to do this. We go around the circle. Okay? Moving on the circle, the actual oscillator is moving this way. Is that? Can you visualize that? Make decent sense? I did one. I don't have a convenient source of light. I haven't had time to do it. I might bring a good flashlight and do this in lab. If we get my favorite piece of lab equipment rotating and have a source of light, let's say we have this over at that end of the room, a source of light over here, then if we put a magnet in a vertical position here, we'll be able to see the shadow of the magnet going back and forth on the wall. And that's going to be a model of simple harmonic motion. That shadow will actually be in simple harmonic motion, even though it doesn't have the mass or restoring force. There's more to this model. So I'm going to take this into my reference vector. Now this reference vector is moving around here with angular frequency omega. Okay, omega equals 2 pi, means 2 pi radians per second. Then we're going to be going around the circle 1001, 1002, 1003. If it's 4 pi, we'll be moving twice that fast. If it's pi over 2, a quarter that fast. Does that make sense? Can you visualize it? Okay, so this is moving around. Then this point on the reference circle has a velocity we call this the velocity of the reference point. Not the velocity of the oscillator, the velocity of the reference point. Well, the velocity of the oscillator is going to be the horizontal component of this vector. So this component of the reference vector is your dx dt, the velocity of your actual oscillator. Does that make sense? You haven't proven it. It's easy to prove. And I'll probably prove it at some point, but I don't want to take the time right now. Okay. Furthermore, you have a centripetal acceleration at this point. Should have given myself more room to label this. It's A sub rel, meaning the centripetal acceleration of the point on this circle. And if I bring my A sub ref over here, right there is the acceleration of the actual object. So my question is, at what point is this component of the reference velocity zero? At what point on the circle? What location of the circle is the x component of the reference velocity, reference circle velocity, zero? Okay, so my question was, at what points on the circle would the horizontal component of this velocity be zero? I got a pretty quick answer, anywhere where you hit the x-axis. And that would be an angle pi, or 2 pi, or 0, or 3 pi, or 4 pi, and an integer multiple of 2. Okay, so integer multiple pi, then b reference vertical. So b is 0. I'll say this occurs at the x-axis, i.e. at the extreme positions of the oscillator. That clear? I mean, match intuition. Okay. Now, if we've got something oscillating up and down, if you wanted to model this in the y-axis and make this a sine instead of a cosine, okay, then you just project this point over onto the y-axis and take the y component of each of these reference vectors, right? And that would match what you get when you take the derivatives of the sine. Then you should actually sit down and do that to convince yourselves. Quite easy. Okay. And not all that easy to convince yourself if it's not something you're used to thinking about, but the mathematics is very easy. Okay, so at what positions would the velocity be maximized? Okay, now I ask the same question about the acceleration. Where is it maximized? Where is the acceleration of the actual oscillator maximized? And I got a pretty quick answer at the extreme points. Why is that? Because you have a centripetal acceleration vector that's of constant length because, again, the velocity around this thing, since omega is constant, the velocity is constant, so the centripetal acceleration is constant. When you're at this point, the centripetal, the reference acceleration, the centripetal acceleration of the point is totally horizontal. So that this horizontal component is maximized. And the same thing at this reference point. And then it's minimized at 0 here and here, because here the acceleration, the reference acceleration is vertical, and here it's vertical, and there's no horizontal component. Okay. So I'll say that V, the actual velocity of the oscillator, don't put a rep on it. I'm talking about the actual oscillator, okay? V is maximized and V is the magnitude of V. I don't have an arrow on it, so this is the magnitude of the velocity vector. And you could call that n plus 1 pi 2n plus 1 pi over 2. That'd be the formula gives you odd multiples if n is an integer. It's not written very big, but that says 2n plus 1 pi over 2. All right. And then we can ask the same question again about acceleration. Okay. Well, now consider the oscillator. It's on a spring, let's say, oscillating back and forth this way. Where's it going to experience the maximum force? What is the magnitude of the force going to be maximized? Well, things pulling the spring back this way, and it's pulling back this way, right? Where is the maximum force going to occur? Should be obvious. It's going to be at the extreme positions, because that's the furthest it can get from equilibrium, and the force is proportional. Magnitude of the force is proportional to distance from equilibrium. Okay. So does that match where the acceleration is maximized? Well, acceleration is maximized out here. It's clear that if there's a spring here, the force is maximized here. And the force is minimized here, because that's the equilibrium position. That force is 0. So this stuff connects. That's pretty much everything you need in order to analyze simple harmonic motion, to analyze the actual motion. Okay. Now you put energy into the mix and you get some extra stuff that you already pretty much have. So we're going to talk about that. Okay. You don't need this picture, but this picture is extremely useful. If you see everything I've said in this picture, if you can reconstruct it and everything, you have a visual connection to all the equations. Okay. And the equations are just the ones do this. Okay. Okay, well, let me shift gears. And talk a little bit about energy. Okay, I've got two of these. Where the others go? I've got a real short on time now. I'm gonna say potential energy is equal to zero at equilibrium. I'm trying to avoid a dummy variable here. My dummy variable is zero because I want X to be my variable here, okay? So we can actually integrate negative KX with respect to X, but I don't want my variable here to match my variable here. So I gotta use something besides that. I could use a Greek psi. That's probably not all familiar. So I'll just use Z. And what's that integral? It's 1/2 KX squared. Okay. That's the work to get from, well, and of course it's negative, okay? It's the work done by a conservative force from equilibrium to X. There, delta PE is equal and opposite, as always, to the work done. For this. So potential energy relative to equilibrium is 1/2 KX squared. So if I pull that mass down on the rubber band, if it's an ideal rubber band, it's going to have a potential energy due to that 1/2 KX squared, whatever K is for that rubber band. Now, again, a rubber band doesn't really have a force constant, and also it's not conservative. A good spring is much closer to conservative. Anyhow, there we have it. So maximum potential energies at X equals A being the amplitude of the oscillation. And as you see that here, it's pretty much automatic. It's pretty much obvious. I hope. So the maximum potential energy is this. At x equals a, d is 0. So kinetic energy equals 0. So sum of potential and kinetic energies is 1/2 Ka squared, not just at the maximum position, but at every position, because the only force is conservative. You have no loss of energy. Okay. So there it is. Kinetic plus potential energy is always equal to 1/2 Ka squared. So if we know K and A, we can find x for given velocity. For velocity for given x. Now, very quickly, since we already find
Yeah.
pendulum of low. Simple pendulum. Here's a massless spring. It's got a length L. And x is its displacement from the equilibrium position, which is vertically below its point of attachment. If x over L is much less than 1, meaning x is much less than L, small oscillation. Okay, well, we've got a tension here. Okay, that tension is nearly vertical. So T is very close to mg. Well, if we draw tension now, draw the mass with the tension, mg, and let's say here's our equilibrium position. So this distance is x. Then well, I can make it better, but I can say that we have a simple proportionality. this triangle is similar to this triangle. So Tx is the same proportion to T as X is to L.
But that takes us.
Little unfortunate notation there. My subscript is X here, but I'm multiplying T by X here. Okay? Because of course, multiply both sides by T. So you get Tx equal mgx over L. The consistent X is in this direction, the tension, when the tension's in this direction, X and the tension component Tx are in opposite directions, so I've got to make one of these negative. So we find that T X is negative mg over L times X. If everything's dissipative, that's all, I mean, nothing is dissipative, everything's conservative, no drag or anything, then this tension is the net force. Because this tension is canceled by gravitation. So we get F net equals negative Kx, K equals to mg over L. You should understand that picture. Very simple statics. And, you know, equipped to understand that picture for most of the semester, okay? So, good picture, good derivation. And wherever I put it, you got the energy relation to this. Okay, that's kind of the whole package. That's all you need to solve, I'll say, most of the problems. I can't think of anything offhand that you can't solve using all that. Now, if you want a pendulum of greater amplitude, then you have to set up a differential equation. And it's not an easy differential equation, okay? Probably, you know, it's one you can probably deal with, but it's not easy. So this only applies for short oscillations. If you get beyond about 10 or 15 degrees from vertical, you start getting significant, although fairly small deviations.